So let me remind you again of our challenge. The challenge we have our kinematical space just of xij's, and we want to find a question whose answer is the amplitude, or at least the tree amplitude for this theory, which is the sum over triangulations of a polygon, the product of 1 over the xij's, with ij in the triangulation. Okay, so so we've gone from airy-fairy philosophy to a very, very sort of concrete question. And now what I want to do is tell you, before getting into what the character of the answer to this question is, I want to give you some hints for what kind of what hidden remarkable properties this answer actually has. That again, I'm emphasizing, we're talking about a seemingly totally boring, dull theory, just this phi cube theory. Okay. Now I want to show you tell you about and motivate why there's going to be something about combinatorics and polytopes and things like that associated with this question. That seems naively crazy. That there's naively nothing about those things associated with this. So in order to do that, I'm going to imagine that I'm an experimentalist. Let's say this is the theory of the world. I'm an experimentalist. I'm living at infinity. And I have a finger on the dial of the Mandelstams that's going to allow me to move the xij's around. Okay. What would I notice? So I'm going to imagine. So I'm going to imagine that I'm an experimentalist. I don't know anything about the theory. I'm an experimentalist at infinity. But I'm going to be experimentalist number 1 to begin. Well, so first, I'm just any old experimentalist. What do you think this experimentalist would notice? In other words, they move. They have their finger on the Mandelstam dial. So as they move the xij's, what do you notice first? And I think it's obvious that the first thing that you'd notice is that this amplitude blows up. It blows up when the xij's go to 0. So that's sort of obviously what you'd notice. The amplitude, at least in the approximation that we're talking about, actually has poles, and it would blow up. All right, so that's obviously very important. And so you could ask what your attitude is towards this. If you're an experimentalist, and now it depends what kind of experimentalist you are. There's experimentalist number 1, who's really a closet theorist. And they say, aha, it's very important. I know, here's my amplitude. I know that when xij goes to 0, there's a pole that looks like 1 over xij. And because I'm a closet theorist, I know that I should care about what happens on the residue of this pole. And by careful measurements, I discover something amazing. I discover that as an xij goes to 0, the amplitude actually factors into the product of 2 lower amplitudes. So it's 1 over xij times the product of 2 lower amplitudes. Or if I say this in the language of the polygon, I would say that if I have these momenta, that if some xij goes to 0, like this one, that the amplitude goes like, so if this xij goes to 0, the amplitude goes like 1 over xij times the product of the guy on the left, the amplitude on the left, and the amplitude on the right. Okay, so this is the amplitude on the left and the amplitude on the right. Okay, so this is clearly very important, and this is factorization. Okay. Notice, what is factorization about? In conventional physical language, it's exactly about locality and unitarity. Locality is a statement of where the poles are. This is that the poles only take place when the xij goes to 0, and not, for example, at 2.3 x13 plus 3.7 x24 goes to 0. Okay, so these are garbage poles that don't mean anything. Only the xij goes to 0 corresponds to a local space-time process. Okay, so locality is where the poles are. So where poles are. And unitarity is what happens on the poles. That's the fact that on the pole we factorize into the product of two lower amplitudes. That's a consequence of quantum mechanical unitarity. Okay, so both locality and unitarity are reflected in this observation of the experimentalist. The poles are in these special spots when the x's go to 0, and they factorize on the poles in order to reflect the rules of quantum mechanics. Okay?
Sorry, can you explain again how the fact that they factorize at the pole indicates unitarity? I understand the locality part, I think.
Yeah, that's really the sort of basic fact that that the only time that amplitudes diverge, even in with harmonic oscillators, is when there's a resonance. And when there's a resonance here, it means that what really happened in this amplitude, the reason it's blowing up, is that this particle in the middle, which we used to think of as being virtual, is actually real. Well, if it's real, then the amplitude should just be the amplitude for producing this guy in the middle, and then having it propagate a long distance. So starting from the in state, producing in the middle, having it propagate a long distance, and decaying to the out. So we have to be able to interpret this amplitude as this particle goes close to being real, as actually being the product of actually producing it in the initial state and having it decay in the final state. Okay, so that's the way unitarity is reflected here. All right, so now imagine that you're a theorist in this audience listening to this experimentalist, and you're very excited about this. So this fact of factorization is clearly a clue to what's going on that this experimentalist has seen. And one theorist sitting in the audience, his name is Feynman. And this person says, oh, I know what's going on. Well, I know. It's Feynman diagrams, which I'm just naming after me. Okay? So it's Feynman diagrams. In other words, Feynman says that what would explain this is if what's going on is that really there's this intermediate in the space-time. I have all these virtual processes. Let me draw a slightly more complicated one. I have this. I have all the different ways that this could have happened, like this. Maybe if I have 6 particles, or this. I have to add them all up. All these things on the inside are virtual. All this stuff is virtual. But this picture manifestly explains factorization. All right, but that's in fact not the only way of explaining factorization. There's another theorist sitting in the audience. It's actually a mathematician. Let's say Pierre Delisle. And he says, oh, I've seen this before. And this is a different setting. If you look at the very, very simplest configuration space in geometry, it's the space of n points on the one-dimensional projective space. 1, 2, 3, up to n. You can think about these as endpoints on the boundary of a disk, modulo the action of the Mobius group. So endpoints on the boundary of disk, modulo SL2. And anyway, it's a famous fact about, as I said, it's a very simplest configuration space of points that you could think of. Notice that the points are ordered because they're in one dimension. They're ordered naturally. And so, so if we look at the simplest case of 4 points, and if you've taken a string theory course, you've seen this. It's very standard basic fact. So let's say I have these 4 points. Then what does the kind of boundaries of this space look like? I can move these points around. This is what it looks like generically. But what happens if these 2 points come close to colliding with each other? Well, you might think if these 2 points come close to colliding to each other, it looks like 3 and 4 are generic with 1 and 2 squashed on top of each other. But in fact, it's possible, as no matter how close 1 and 2 get to each other, we can always undo this with an SL2 transformation. And then what I'm left with is 1 and 2 back far apart from each other, but 3 and 4 squashed close together. And therefore, there's the boundary of this space. The boundary of the space of 4 points is actually has this remarkable factorization, sometimes called the bubbling picture. Or factorization. So it really looks like there's kind of one world in which 1 and 2 are far apart, another one where 3 and 4 are far apart, but in this world, this intersection point from the perspective of 3 and 4 is 1 and 2 squashed together. In this world, it's 3 and 4 squashed together. Okay, and this is true for general N, that the boundary, so the boundary of this space of N points on a disk actually factorizes into N1 points and N2 points. The intermediate point here representing all the rest of one side, this side, or this side squashed on top of each other. Okay, so Deline sees this and says, oh, I've seen this before. In other words, what this experimentalist has seen is some structure where the singularities of this thing look like the product of 2 lower guys of the same form. And Deline says, well, that's exactly what I've seen before. I've seen that I have endpoints on the boundary of a disk, and this space on its boundaries factorizes into the product in exactly the same way. And in fact, this observation gives rise to another way of explaining factorization. And this is, in fact, what string theory does. So if I summarize, if I look at factorization as the star, then there is one picture, which is the picture of particles in space-time. There's another picture, which is the string worldsheet. And these make factorization manifest. So it's sort of fascinating that the two basic frameworks of the past 50 years that we've had for understanding scattering processes, either as particles in space-time or associated with the string worldsheet, their purpose in life is to make factorization totally manifest. Okay, so great. That's wonderful. Is there anything left to be desired? Is there anything missing in our understanding? I mean, yes, we know about factorization. It's all in the textbooks. We know. Is there anything missing? Well, there is something missing, in fact, and that's going to be the star of the rest of our a lot of the rest of our discussion. In order to see what's missing, let's go back to a second kind of experimentalist who's lazier. So we want a lazier but smarter. Well, since this is my story, I'm going to make them. The hero. They're not a closet theorist. They don't care about poles and residues or any crap like that. Okay, and their attitude is different. They say, look, I've seen that they get excited about the fact that the amplitude blows up, but they ask, so this experimentalist number 2 asks, how do I make it blow up more? So for instance, at 4 points, n equals 4, if I revert to standard notation for a second, just for convenience, they notice that there's a pole at s equals 0. And then they say, great, can I make it blow, can I make the amplitude blow up even more? And then they move the dials around and they see, no, they can't. Okay. Or as t goes to 0, but then when they put t to 0, no matter what they do with s, they can't make the amplitude blow up more. However, they'll notice that if n equals 5, that if they send s12 to 0, that they can also send s123 to 0, for example. Okay. And secretly we know that's because it could come from a diagram like this. Also, they could also send s512 to 0, and that would come from a different diagram, right? It would come from a diagram that looks like that, 5, 1, 2, 3. Okay, but in both cases, 1, 2 is 0, but also okay, so we can have these we can have interesting patterns in the poles that can appear together, right? They're not random. At 4 points, if I have s, I can't have t. At 5 points, I can have s12 and I can have s123, but I can't have if I have s12, I can't have s23, and so on. Okay. Now, so they might want to present this data, and now let me actually draw it in the language of the polygons. Okay, so what we're saying, let's say it's 5 points, is if we have x13 goes to 0, then I can have also, if I have x13 goes to 0, then I can have this guy go to 0. I can have x14 go to 0. I can also have this guy go to 0. Okay, so if this is 1, 2, 3, 4, 5, I can have x14 goes to 0, or I can have x35 goes to 0. If x13 has gone to 0 to begin with, those where I can have poles. Remember, the poles that we see correspond to triangulations of this polygon, but I can't have these I can't have these incompatible poles that would correspond to chords that cross. So I can't have 1, 2, 3, 4, 5. If I have 1, 3 goes to 0, I can't have 2, 4 goes to 0. This is not allowed. All right. So it's interesting. There's some interesting sort of combinatorics into what poles can occur together. And this experimentalist might want to present what that data looks like. So they would notice for n equals 5 that there's a very cool picture that they can draw. Now this is just a picture. Completely coincidentally, the picture looks like a pentagon. Okay, more generally, it'll look more interesting, but I'm just starting in this case. This is a picture, and I'll explain what this picture is in a second. This picture is meant to indicate what the single and double poles are. So you see here, this edge reflects the fact that there's that single pole. This vertex reflects the fact that I could have two different, so let's say this guy here is that single pole. And this vertex reflects the fact that I can have both of these single poles. So you see, that vertex is now a complete triangulation of the pentagon. The edge is a partial triangulation, but the vertex is a complete triangulation of the pentagon. And I can keep going. Okay, so I can keep going to finish this picture. So for instance here, I can have this guy and that guy, and so this edge would be that one, and so on. I'll leave it for you to finish the rest of the picture. Okay, so you see, it's very interesting that the pattern of the poles that can occur together, the pattern of poles is captured by a shape. Is captured by a polygon in this case. That's pretty interesting. That's sort of not obvious ahead of time. Now, what does that look like for n equals 4? For n equals 4, we would just draw this, right? We would just say on one side, we just have this triangulation of a square. On the other side, we have the other triangulation of the square. So this picture is pretty boring, but still we can draw it. So I'll just draw partially the pentagon again. So on this side, we'd have this guy, and then the vertex would be the complete triangulation, and the edges would be partial triangulation, okay, and so on. In fact, you can sort of imagine that the interior is the whole thing that's not triangulated at all. So then we have a uniform picture where we have the interior not triangulated. The first boundary is triangulation with one chord, the second triangulation with two chords, and so on. Okay, now does this pattern persist? Well, already for n equals 6, it's a little bit complicated to visualize. For n equals 6, how many poles do we end up getting? We can get up to 3 poles together. So that would give us a 3-dimensional picture, if there is one. And okay, this experimentalist may not be so keyed in to be able to figure out what the picture is. But let me just give you, before showing you there is a picture and what it looks like, I just want to emphasize how non-trivial it is. They don't have the good geometric imagination to draw this 3-dimensional picture, but they can at least count how many single poles are there, double poles are there, triple poles are there, and so on. And this is the data that they would get. For n equals 4, they would find that there's 2 single poles, right? 1 over s and 1 over t. So this is one pole. For n equals 5, they find 5 single poles and 5 double poles. For n equals 6, if they just count, they would find 9 single poles, 21 double poles, and 14 triple poles. For n equals 7, they would find 14, 56, 84, 42. For n equals 8, they'd find 20, 120, 300, 330, and 132. Okay, for more and more poles, 3 pole, 4 pole, 5 pole. Okay, and now you can ask from this data, could there be a shape? And what are we looking for? We're looking, let's say, for n equals 6. We're looking to see, could there be a shape where all of these single poles would be the faces of the shape, and all the double poles would be the edges of the shape, and all the triple poles would be the vertices of the shape. Okay, and even without knowing what it looks like, you can do a very quick check to see if this is possible, which is if there was a shape, we'd have to have the number of vertices minus edges plus faces would have to equal 2. And if you do this calculation, 14 plus 9 minus 21, it's indeed equal to 2. And amazingly, you can do this calculation for the other cases. And in all the cases, you see that this Euler sum works out so it's at least possible for there to be a shape. Now, that's totally unobvious ahead of time that there is these, it's totally obvious. It's not at all obvious ahead of time that these identities should be satisfied, but they are satisfied. So there is, in fact, a shape, and I want to show you what the shape looks like. So let me transition back for a moment. All right. So this is what the shape looks like, and it's known as the shape is known as the icosahedron. It was discovered by Jim Stashev in the 1960s, and so this is an example of what it looks like. I've drawn it in Feynman diagrams now. So you see this, it's cool 3-dimensional shape. I've only labeled the vertices of the shape here in terms of Feynman diagrams.
I don't think we can see the shape.
We don't see it.
Sorry, are you not? Is this not? Hold on a second. Oh, sorry. I know what happened here. I apologize. There we go. Okay, can you see it now? Good. So,
Yeah.
Yes.
okay, so So you see that I've only indicated, labeled the vertices of this shape with cubic diagrams. You could go and label the rest of them. So the faces would just be a single factorization with just one particle in the middle going on shell. The edges would be two particles going on shell. And you see two vertices here, so two cubic diagrams would be related precisely by going from one channel to another. So two graphs are connected by an edge here. If they're related by taking some intermediate process here, imagining going to a partial factorization where this guy actually collapsed to a 4-point and then factorizing again the 4-point from the S channel into the T channel. Okay, so this is really non-trivial that such a shape exists that captures the combinatorics of all the poles of the amplitude. Right. So this is a fact that's not obvious in the Feynman diagram picture. It's not obvious in the particle picture. It's not obvious in the string picture, manifestly. But it's an interesting fact. This is what the second experimentalist gets excited about. And so we are going to try to make these facts obvious. It's not obvious in the textbook ways of understanding understanding this very basic physics. And in fact, this picture also knows about factorization. So it knows more. The way it knows about factorization is the following. So so if you notice this three-dimensional shape, it has 6 faces that look like pentagons. Here's 2 of them, and you can find the rest of them. And it has 3 faces that look like squares. Okay, so this one, that one, and that one. And in fact, this facet structure of the isosahedron captures factorization. Remember, we just saw that the 5-particle amplitude is captured, its combinatorics is captured by the pentagon. And so we see the pentagon here as a face. This corresponds to a factorization of the 6-particle amplitude, where on one side you have a 5-particle amplitude, and on the other side you have a 3-particle amplitude, which is sort of nothing here. Okay, so the fact that you have 6, the geometry for the 3-particle amplitude would just be a point, if you like. For the 4-particle amplitude, it was a line. For the 5-particle amplitude, it was a pentagon. So each one of these pentagonal faces are telling you about the fact that the factorization of this object is into lower objects of the same sort. It factorizes into a pentagon times a point. These 3 things that look like squares are just an interval cross an interval. And those are the factorization of the 6-particle amplitude with a 4-particle amplitude on one side and a 4-particle amplitude on the other side. Yes. Is there a question? Is there a question, guys, about this? Okay.
Enrico had a question.
Yeah. Oh, Enrico, yes.
I had to through myself. I have a question. So what you were describing at tree level, that's like exactly the Steinman conditions, that you can't have overlapping poles in overlapping channels. Is there a generalization to that for 2-particle invariance to loop level?
We're going to be talking about the generalization of all these things to all loop order. Certainly at one loop, and yeah. So you will see. The answer is yes. But,
okay, so I'll just wait.
But at the level of the integrand, it's pretty obvious. What the conditions are obvious. The fact that they're geometrized is not obvious, of course. It's not obvious even here at the tree level. So in other words, the word Steinman relation is not buying you anything here. I mean, yes, it's true, but it's also trivial at the level of the starting from the normal picture of Feynman diagrams. It's totally obvious. We don't have these overlapping channels. That is obvious. What's not obvious is that the pattern of poles that can come together are captured by a polytope. That's totally unobvious. And as I said, I gave this example of just doing the counts. The fact that these Euler sums add up to 2 or 0 appropriately is just not obvious from this picture of the diagrams. So that's going to be our goal now. We want to figure out how to make this picture obvious. In other words, what we want to make obvious is that the whole structure the combinatorics of the pole structure is polytopal, and that the polytope has the property of factorizing on the above. Okay, so that's what we'd like to understand. Okay, let me pause here. So oh, sorry. There's one more thing. So sorry. Okay. So that's one qualitative fact. There's one qualitative fact about these amplitudes is that the pole structure is polytopal and it factorizes into itself. There's another fact that there's actually a hidden symmetry. Of scattering, not quite amplitude, but as we'll see, form, scattering form. All right, so let's now talk about this. So, so this again in the spirit of data of things that we're going to try to explain. Okay, so let's go back to the case of n equals 4, and again think about the amplitude as we ordinarily would, as sort of 1 over s plus 1 over t. I'm reverting again to ordinary notation, or 1 over x13 plus 1 over x24. Okay, that's perfectly fine, but we're going to find it interesting, and we'll talk about this more at length, to think instead of this function, the amplitude as a function, we're going to think about a scattering form, a differential form instead. And what is the form going to be? The form is going to be, it's sort of obvious what you want it to be. Here, instead of having 1 over s, it'll be ds over s. Instead of having 1 over t, it'll be dt over t. Okay, and of course you know about forms that the signs of wedging things matter. We're not wedging anything here, but signs matter when you have forms. So now there's a question. What sign should we have here? Should we have a plus sign, a minus sign, what? So what sign should we have? And there's actually a cool answer. We want the minus sign. And I'll say what that accomplishes. We want the minus sign. And the reason is the following. You see, we might like it that the form only depends. S and T have units, right? So we might like it the form only depends on the ratio S over T, not on the overall scale of the units. What that means more formally is if I think about S and T as a two-dimensional, as a 2-vector, if I group them into a 2-vector, then I want to have invariance under a projective, under the transformation that would make this a projective space, so that ST goes to any rescaling, any function that could depend on S and T of ST. See, obviously S over T is invariant under this. So if we could accomplish this, it would mean that this form only depends on the ratio of S over T and not on the overall size of S and T. Now, is this possible? If I take ds over S plus dt over T, then this is manifestly false. But if I take ds over S minus dt over T, then you'll notice that I could write this as d log of S over T. And that does satisfy this property. Okay. Now, okay, that looked a little bit trivial, like we could make a choice, so we made the choice. But let's actually do the next example, where life is already more interesting. And let me actually state what the problem is in general. So we're going to have some omega at n points. We'll have n minus 3 is the number of poles that we have. So we're going to have an n minus 3 form that depends on these xij's. But we want it to be invariant under xij goes to alpha of x times xij. And the form will be built out of things that look like dxij over xij that I can write as d log of xij. And under this shift, d log of xij goes to d log of xij plus d log of alpha. And so you see, this is the dangerous guy. I don't want to have any dependence on d log alpha because I want the form to be invariant. So I want under this shift, under x goes to alpha of x, I want the form to just go back to itself. So that means that the coefficient of d log alpha should be 0. All right, let's see how this works. So let's say I go to n equals 5. So this is example still almost trivial, but already shows you that there is something not non-trivial going on. So naively here, the amplitude would be 1 over x13, 1 over x14. These are just the triangulations of the pentagon. And in this case, there's just 5 of them. This one plus all of its cyclic rotations. So to have this plus cyclic, right? So that's the amplitude. So what's the form? So let me now write down the form instead. So the form, but I'm going to be agnostic on the signs, is dx13 over x13, dx14 over x14, and let me write all the rest of them down. So I'm just going to cycle everything over one. dx24 over x24, dx25 over x25, dx35 over x35, dx31, which is the same as 13, so I'll write it like this, and then dx41, which is the same as 14 over x14, dx42, which is the same as 24 over x24, and finally dx25 over x25, dx 35 over x35. Okay, so these are the 4 things that I can have, and I want to see what happens as I take d log xij and I replace it with d log xij plus d log alpha. And you see what's going to happen is that every single term is now going to, if I had a d log x, d log y, it's now going to have a piece in it that's like d log alpha, d log y from one of them, and then from the other side, d log x, d log alpha. And I want all the dependence on d log alpha to cancel. So, so that's what we want to see. So let me just keep this all in our field of view. So let's look at the coefficient of, d log, let's look at the coefficient of d log alpha times, let's say, d log x14. Now, where do I get that? I get this from this first term. So let's say by convention, I'm going to put a plus sign here. The overall sign doesn't matter. So from here, I'm going to get a d log x14 from dx1 when d log x13 is when d log x13 is replaced by d log alpha. And so something has got to cancel that. Where else can it come from? Wherever else I have a d log x14, like here. Here I have a d log x14. And so you see, if I put d log x24, if I put the d log alpha there, there's something that could potentially cancel, but it can only cancel if there's a plus sign in front of this guy. Okay, so if I have a plus sign in front of this guy, the d log alpha from this cancels against the d log alpha from that. Remember that the wedge product is antisymmetric. Okay, so in order for the coefficient of d log x14 to be 0, I've succeeded in doing that by making these two have the same sign. Let me keep going. What about the coefficient of d log x24? Well, okay, here's one. We have one here. Where else do we have it? We have it there. So again, I have to have a relative sign. Well, they have to both be a plus, so that saves that guy. Now let me go to d log x25. So we have this one already. Where else do we see them? We see them here. So once again, they have to have a plus sign in order for the variation of this to cancel against that. Okay, let's look at d log x35. Okay, well, where else do we see the d log x35? We see it here. So again, we have to have a plus sign. So we've saved that. But now you see, now we're done. We have determined all the relative signs. So there's no more freedom. So, but there's one more thing to check. We have to check whether d log, the last guy that we haven't checked is d log x 13. And phew, thank goodness d log x13 works, okay? Because there's a cancellation between this term, this plus sign, and that plus sign there. But you see, this was not guaranteed by equation counting. It was not guaranteed. Just in the 4-point case, it was guaranteed by equations and unknowns. In here, it is guaranteed. Sorry, it was not guaranteed by equations and unknowns, but it turned out to be true anyway. And as you go to higher points, this gets more and more remarkable. There are more and more equations that have to be satisfied with fewer and fewer unknowns. So it's not remotely guaranteed by equation counting, and yet it's true. It's true that it's possible to choose the signs in order for the amplitude to be projectively invariant. So this is a hidden symmetry. Projective invariance. Okay, this is the analog. It turns out this is really a kind of a precise analog of the dual conformal invariance of n equals 4 super Yang-Mills. But now just for this dumb old phi cube theory. So this dumb old phi cube theory has this hidden symmetry, and it's really interesting, and you can really check it for yourself. It is impossible for any subset of the diagrams to be given signs to work, to be projectively invariant. You have to add all of them. And you have to add all of them with very specific signs. In that example, it looked a little trivial because they're all the same. In general, the signs are interesting and different between different kinds of topologies of graphs. So this is an example of a hidden symmetry of this form. It's not obvious in Feynman for each graph. In fact, each graph doesn't even have it. It's only a property of adding them all up together. Okay, and so this is another sort of qualitative fact about the amplitude that that we have to try and understand. And I'll make a final comment, and then we can stop for another break and questions. The other comment is that how do we go? There's one last bit of magic. How do we go from this form to the actual amplitude? Okay, so the actual amplitude we want is 1 over s plus 1 over t. Here we have this form that looks a little far from that. It's ds over s minus dt over t. And let's say for 4-point scattering. And let me tell you what the answer looks like in this case. And once again, we are going to try to understand how all of this arises more systematically. But in this case, it's very simple to say. You see, here we have a 2-dimensional space, S and T. Okay, so this is our canvas. In this case, we just have this ST space. And but the form that we're looking for is a 1 form. Okay, this is ds over s minus dt over t. And how do we go from this form to the amplitude? Well, it's a 1 form. So we need to find ourselves some 1-dimensional space, subspace in this 2-dimensional space. Well, there's a natural 1-dimensional subspace we can talk about. Let me draw it like this. S plus t equals constant. Okay. Now, what happens when you take this one form and you pull it back to the space where s plus t equals a constant? That literally means you just shove s plus t plus constant equals constant into the form. What do I get? I get ds times 1 over s plus 1 over t. Okay? Because the minus dt is equal to plus ds. Okay, well, of course, this t is also equal to the constant minus s. But you see, quite beautifully, we managed to find a subspace. We found a subspace where omega equals just the unit sum, the volume form on the subspace multiplied by the amplitude. Now here we just found it by inspection, but this is going to happen in general as well. And the fact that it's possible to take this form of all the plus or minus signs and to find a subspace so that when you pull it back to the subspace, you get the volume form out in front, and then a formula with all plus signs that's equal to the amplitude is another non-obvious fact, but which will end up being the case. All right, so let me summarize. So if we imagine that we're this experimentalist at infinity who just has their hand on the Mandelstam dials and is moving things around, any such experimentalist with a pulse will first notice that the amplitudes have poles. And you might get excited about the fact that they factorize on those poles. And the fact that they factorize on the poles is the purpose in life of the particle and the string picture of scattering amplitude. So factorization of the star, particles and strings are what make those manifest. However, there is this laser experimentalist who just cares about something more basic, like how much could you make it blow up more? What are the patterns in which the poles can come together? And they noticed something. They noticed that there is a remarkable geometric structure, a combinatorial and geometric structure of the way the poles can come together. That's not obvious at all, but once you see the structure, it also implies factorization, because that structure of this associahedron actually factorizes on the boundaries. And it factorizes the facets, the faces are direct product of lower associahedra of the same type. So that's one qualitative fact, not in the textbooks that we know of. It's a qualitative fact about amplitudes. Again, not just of this theory, but really any theory that has this, that at least has this ordering associated with it, has this universal kind of factorization properties, and that's and the combinatorics of the poles is polytopal, and that polytope factorizes the lower polytopes of the same kind on its facets. So that's one remarkable fact. Another one is the hidden symmetry of this scattering form that's possible to be made projectively invariant. Someone asked why we care for it to be projectively invariant. At the moment, not obvious why we care about it. Other than that, it would be kind of strange for the form to care about the overall scale associated with the variables. It's obviously nicer for it to only care about dimensionless ratios. As we'll see, this is related to this is a sense in which it's analogous to dual conformal invariance in n equals 4 super Yang-Mills. It's related to the fact that the amplitudes have a surprisingly good behavior as you go off to infinite momentum. They're softer than you would naively expect from diagram by diagram as you go off to infinite momentum. But it's just an interesting fact. At the moment, it's an interesting fact. So the fact that the pole structure, the combinatorics of the pole structure is polytopal, that it factorizes, the fact that there's a hidden symmetry of the form, and the fact that it's possible to find a subspace on which this form, all the minus signs disappear and we just get uniformly all plus signs and we get the amplitude. These are all qualitative facts that we're now going to try to make manifest. Okay? And let me just give you an idea for the sort of plan for the rest of the lectures. We'll see when either you guys drop or I drop. I've been told by the bosses that our 4 hours are a little bit relaxed. But anyway, I'm in no particular rush. But let me tell you at least some of the things that we could talk about or what my plans were. The next thing that I wanted to talk about is before getting to the, so this is the plan. Before getting to going back to this kinematical space and talking about the kind of questions that we're going to ask there to make these things obvious, I wanted to back up and tell you a little bit more about positive geometries and canonical forms. So just some generalities here. And because again, and so I'll explain what these canonical forms are, but also tell you what stringy canonical forms are. This is a recent way of thinking about these forms, which is interesting, and we'll have a number of important applications. After we do that sort of interlude, we will talk about, after we do that interlude, we'll go back and talk about the question in Xij space. So we're going to go back and we're going to discover that there's a remarkable structure in this kinematic space. That kinematic space, this kinematic space of Xij's is its own space-time. It's a 1 + 1 dimensional space-time. It has a notion of causality and in fact causal diamonds. And that all of this is going to associate in kinematical space-time. We're going to see the isosahedra and generalized isosahedra. And these things are also known as cluster algebra polytopes. Now, I haven't told you anything about cluster algebras, and up to this point, you don't need to know anything about them either. And I won't be telling you about them in this part. We're just going to be playing interesting games in kinematic space, asking simple questions and seeing the sort of remarkable space-time causal structure emerge in kinematical space. And that will lead us, as we keep asking natural questions, to discover both the isosahedron, generalized isosahedra, and the connection to cluster polytopes. When we see all of this, we'll see that we'll get a story of these geometries. You can think of these amplitudes for the phi cube theory, which is just the isosahedron that we talked about at tree level. But in fact, it will go through to one loop. So we'll go through to one loop. At one loop, it'll end up being one of these cluster polytopes. Okay, so you'll see what this means later, but it's the DN cluster polytope. Again, you don't need to know anything about cluster algebras for this part. We're just going to be playing, and we'll run into these objects naturally. Now, the amplitude is going to be associated with this notion of a canonical form tied to these geometries. And we'll actually see there are many ways of computing these canonical forms. So if one way of computing them, one way of computing omega will be Feynman diagrams. It'll give us back Feynman diagrams. But there are many others. And the other ones will make other properties obvious that the Feynman diagrams don't make obvious. And finally, when we apply this general formulation of stringy canonical forms to compute the canonical form for these polytopes that we're going to find, we'll actually discover string amplitudes. Okay, so that's the story for the so that's the second thing. After all of this, the third thing that I wanted to talk about is just an introduction to cluster algebras 101. So we'll go as far as we can without saying anything about in detail about cluster algebras, but it really pays to know what's going on from the cluster algebraic point of view. I'm not going to assume you have any previous knowledge of these things. I won't tell you everything about cluster algebras, but I'll tell you what's needed, enough that is needed to actually start working and playing with these things. And I will tell you why there's a deep connection between cluster algebras, at least one origin of deep connection between these cluster algebras and very basic physics of space-time and quantum mechanics. Okay. And we'll also understand how our previous constructions and discoveries are related to this. And there are two final topics, which are broadly taming the infinite and one of them is towards the all-loop generalization of these stories for the phi-cubed bi-adjoint theory. That's what my friends and I have been working on for the past couple months. And also some words about towards the non-perturbative geometries for n equals 4 super Yang mills. Okay, so that's the whole list of things that I've prepared, and we'll see what people are interested in listening to, how far we get. But again, I'm in no particular rush. You guys can feel free to disappear whenever you want. And obviously, if my voice gives out at some point, we might have to stop then. But all right, so that's it. Should we take a break for 5 minutes or so?
Great, thank you. There's some maybe questions. Yeah, let's take a break until 12:30.
Okay.
So get back 12:30.
Great.
Sounds good? Perfect.